Okay, so welcome to the second half. Welcome to the second half of this class. Right. So the first half went a little bit about a little bit insights of at some point I'm going to be giving you a little bit more um, historical background, how we came up to quantum mechanics and how quantum mechanics, the mathematics is quite involved, but the mathematics of quantum computing is quite simple. And in fact, that's the original inspiration for me providing this as a kind of like a gen ed class, is that ultimately all you need to know is linear algebra. Okay, that's it. That's it. If you don't know linear algebra, you can take this course and you can do well. Now, the reason I'm introducing the Wolfram Mathematica is because, as you will see, linear algebra, even with linear algebra, it's going to be more painful to do by hand. So it's going to be much nicer to do with a computer, right? And not only that, like I said, Mathematica was created for physicists as a general language for computation, and it works really well for physicists and mathematicians. And then as different community come on board, like chemists, so there's a big library of chemists. Now, the original physicists using Mathematica would have to program everything by themselves. And now the big community of quantum computing research came on board. So now we have a big library. In fact, I would not even say a library. I would say it's its own platform called Wolfram Quantum Framework. Okay, and that thing is really to me anyway, is the future of doing this algorithmic side of quantum computing. And so we will introduce you to that. So this class starts out with telling you that Mathematica, think of it as a functional programming. Okay, much like some of you who are familiar with Python. The idea with functional programming is that, like you point out, it's a bit iterative, so you don't have to compile the whole thing. But the key thing that I want to make is that you communicate with it by making requests, but you don't request in a sentence. You request by calling a mathematical function. Okay, that mathematical function usually doesn't have just f, because it means nothing. It doesn't mean, so those mathematical functions that are built in will have an English sounding name like plot, show, manipulate. Okay, so it's f. It really is f. Okay, but if you write f, well, what does it mean? Doesn't mean anything. So the function will usually have an English meaning, plot, this and that. Okay, now you are not going to be satisfied, or you when you use your own code, you are going to use the built-in function together, string them up to make your own code. Okay, like I said, the analogy would be there's a built-in function for beating egg, there's a built-in function for adding flour, but there's no built-in function for making a souffle. So you have to define your own function called souffle, and then supply it with the ingredient. And within that function, in the body of the souffle function, you will call a function called beating an egg, adding flour, mixing whatever, add salt, turn on the oven or whatever. Okay? So basically, that's what functional programming does. And as a side track to Mathematica universe, I show you that there is this thing called Wolfram Alpha, which is kind of like turning Wikipedia into computable database. Okay, but it's not the same database as Wikipedia because it's curated. Wikipedia can be changed by the public. The information in Wolfram Alpha cannot be changed by a public, so it's curated within the closed system. By the way, that's why you have to pay, because it's a closed system that people develop and all that. So with that, then I also told you about the entry. When you open up a Mathematica notebook, you see that it looks just like uh, this Jupyter notebook. And when you enter some command, it's going to be interpreted as a function. But as I found out during the break, some of you guys default as text. So when you enter plot, it doesn't do anything because it's the word plot. Okay, right. Okay. Now, like I said, this is a reference page. In fact, you don't need to go to Mathematica to open this. It's called reference.wolfram.com, right? So if you did this reference.wolfram.com, it's going to bring you to this huge page. It has everything in it. Okay. Now let me just briefly point out what you got. Okay. So first of all, I don't like this tab. How can I get rid of our tab? Can I? How do I get rid of this tab so I make room? Never mind. Okay, core language structure. Again, that's how do you define a function? How do you blah blah blah? Data manipulation and analysis. That's what I use quite a lot because I teach data analytics. Visualization is where we are. This is why we're using. Okay, so we're using Mathematica because not only do we want to use linear algebra, okay, we also want to visualize it. Okay. Now, Mathematica has a whole bunch of machine learning, large language model in there, but we're not going to use that because this is not our concern. I will show you a little bit of symbolic, just to all kind of stuff: graph network, string text geometry, image, picture. Again, as more community comes on board, like cultural data, this is something that I never use. Okay. Right. So let's go to here. Now, this is something that is supposed to impress the heck out of engineers. How many engineers again we got? Okay, you know what the differential equation function is? Of course. Well, this is how you define a function. Okay, what? Okay. Now, the rest of you just take a tour of this, because what it does is I define a function. I call this thing a heat function. Okay, heat function means this. Make it bigger. Oh, sorry. Get rid of this thing. I don't know why. One minus. Okay. Right. Now, heat function is basically, well, a function assign a value f or y to x, right? Now, think of x as a location. Okay. Location from 0 to 10 meters. Okay? Think of f of x as a function that tells you the temperature of a steel rod. Imagine we have a steel rod here. Steel rod. Okay? From here to there, this steel rod has heat, and heat has to dissipate. It's not like a temperature of the room where the whole room gets the same temperature. So you can imagine I have a steel rod here, right? And I take a lighter, and I put the lighter over here. It's going to get hot here, right? Right? And the heat's going to dissipate. Okay? Now, the function of heat dissipation is very advanced. People who make a living as automotive engineer, they study combustion cycle, all kind of stuff, right? But at the end of the day, it comes down to differential equation. Now, you don't know what differential equation is. It's basically equation that relates some quantity with its rate of change. Okay? And it's calculus. It's basically calculus. It's the thing. Now, in most computer program, you can do differentiation numerically. In other words, you get a slope, and then you estimate the slope. Mathematica can do it symbolically. So I define this as a heat function. Then I define heat equation, and this is second year engineering, as a partial, you see that little thing? Partial with respect to t of a heat function, and partial with respect to x twice of the heat function. It doesn't mean anything to you. But that's what physicists discovered heat behaves. The rate of change of temperature is proportional to the second derivative of the difference in temperature. So partial t is equal to second partial x. And then let's see what happened. This is purely symbolic. So as I define this, it would be able to do this symbolically. Now, doesn't mean anything to you right now, but I'll show you how it works in a little bit. Make a note. In all programming language, doesn't matter if it's Python, C, blah, blah. Not only does it have built-in function, it has a built-in way of storing information. Those are called data structure. Okay, so when they say x is equal to 5, this data structure is the simplest. It's one variable. But imagine that I don't want to work with one variable. I want to work with a list of variables. So I want to refer to this thing as x, y, z, 3 numbers at the same time. Okay, that structure, that list, is basically called a list. And that's the most common data structure there is the foundation. So first thing is a variable, second thing is a list, then everything is built on there. Good example would be your matrix. Your matrix is an array, right? x11, x12, x13, x21, x22, x23. Well, how would a computer store that? Basically, it's a list of lists. It's a list of rows. Okay, so let's show this. So in other words, so x is equal to 5. So this is a data structure, just one variable. Okay. Now, what if I don't say x is equal to 5? I say x is equal to A, B, C, and D. This is what I mean by data structure. Okay. This data structure is called a list. So now I can say, instead of assigning this, I can say x is equal to 5, 1, 2, 3. I can do that. Okay, that's a list. Now, what is a matrix? You guys remember the matrix from last time? Right? So let's call it A, B, C, D. Right? How would Mathematica, or in fact Python, store this? It doesn't store it as two-dimensional array. It stores it as list of list. So what it's going to look like is my matrix is equal to list A, B, C, D. See that? It's a list of lists. It's a list of rows. Okay? What else? Well, you guys are in modern time, right? You hear the word tensor a lot. It's an abuse of vocabulary, by the way. What it is, well, yeah, you can call it tensor. Okay? What are you looking at? Computer screen. What's a computer screen? It's a array of pixels. So instead of having 3 rows and 3 columns, you have, I don't know what the resolution is. Let's say this is 1080 or whatever, okay? And this is 5000. All it is a list of 5,000 objects, of 1,000 objects. Each object itself is a list of 5,000, right? Unfortunately, with this, you can only do black and white, right? 1 being white, 0 being black, let's say. How would you do RGB? You use 3 numbers. So what is a computer screen? A computer screen is a list of a list of lists. Okay? See that? A computer screen is a list of lists of lists. The first list talks about the top pixel, right? The second just go from the leftmost pixel to the rightmost pixel. And what's the inside this? It's the value for RGB. 0 to 63 or something like that. Or 0 to 1. Okay? So this is called a tensor. Now, technically, tensor means a lot more in physics. But, popular vocabulary call this tensor, which is not wrong, but just a little bit too fancy, I think. Okay? So that's called a tensor. So each screen is a tensor. One of the most important library, okay, that came after 2012, it's called a library called TensorFlow. Basically, it just passes information that looks like a screen. That's why you do this visualization picture, right? Like cat recognition, dog recognition. All this comes from the fact that a cat and a dog is ultimately a tensor. The picture is a tensor, right? With the number of rows equal to the number of pixels along the horizontal and along the vertical, right? What's a video? It's a list of lists of lists of lists. Because now you have one for each time frame, right? So you have 120 of those per second. Okay? So it's a list of lists of lists of lists. That's a video. Does that make sense? Okay, that's how you store video data. Well, no, not really, but conceptually. Okay, so list is very important. And not only does Mathematica have a reference definition of list, sometimes because it's so useful, they also have a guide. Like in this case, it's called a guide. So that gives you like a workout example and interesting thing and all kind of stuff. Yeah. So it's not just giving you the. So now the important thing is in Mathematica, a list can be a bunch of things. Can be a number, can be value, blah, blah, blah. So all this, okay, this is my homework. Okay, all this. Now, a list, like I said, you can refer to the whole list, right? So a list is convenient because if you have 10 numbers, you don't have to write each one of them, right? You just refer them by the whole list. But alternatively, or on the other hand, what if you want to access individual number, right? So let's do this. So I define X is equal to A, B, C, and maybe 7. I don't care. Okay? How do I get to this guy? To say I want the second element. So a list, very important, is an ordered set. So this is not the same thing as 7A, C, B. Right? It's not the same. Right? So, someone who's 6 feet tall and has 38-inch chest, that's a human being. But somebody who is 38 feet tall and 6-inch, that's a ghost, that's a pret in Thai, right? So definitely not the same thing. So order matter. Now, how do I get to this? To get to this, I use double bracket. So type in, see if you can do this. So X is equal to A, B, C, D. And type X3. It's going to give you C. Now, Mathematica does something cute. Instead of double bracket, it's just going to squeeze it together into this thick bracket. You got that? Okay. So list is the most important data structure you need to know. Mathematica start from 1. If you have a bad habit, not bad habit, if you have a habit from Python, remember, it starts from 1. Okay? Why is that? Well, it's more convenient for mathematics because the last element is the same as the dimension. All right? Think about it. X1, X2, X3. The third one tells you that, well, if there are 3 numbers, they're 3 dimension, as opposed to 2 plus 1 dimension. Okay? Yep, you should double. Okay, if it's a text, it's not one. Okay. So, that's it. Now, one of the most useful way, okay, this is accessing individual item. Okay. A list of lists, see that? RGB, red, green, blue. So type in this if you want. See? RGB, red, green, blue. Now, if I want individual one, like 2, 1, what's going to give? Okay. The answer, by the way, I'm not quite sure how the midterm is going to work, but what I might do is just make life simple and just use paper. And I'll just say, okay, if that were this, what am I going to get out of this? All right. So obviously, if the bracket gives you the element, and in this case, I have lists of lists, so the number 2 is going to refer to what? Second list. Number 1 is going to refer to what? The first element of that second list. So basically, you go down to 2, and then you go down to 1. Okay? So what are you going to get? Anybody? Right? Go to the second, then go to the first. Okay? Now, obviously, this has to match. So if I put RGB bracket to 7, it's going to return error because it's beyond it. Okay? So that's called accessing. So that's easy. Now, this is a lot of this is I talk a little bit about functions. So these are details. Okay. But just to show you that things work easily, again, I like to give example where, you can do so in Python in 5 pages. Okay. So here I'm just drawing some distribution. This doesn't mean anything, but in statistics, you know what it means. Blah, blah, blah. Now, this is where I want you to pay attention. One of the way, if list was small, x is equal to a, b, c, d, you just use a, b, c, d, right? But if x is 500 numbers, you would refer to them by maybe index, right? So something like this. This table here, table is one way of creating a list. Okay, so what do you think happened in the first one? First line, table I, comma 5. Just guess, common sense. It's going to create a list of number I. That number I going to 5. Now again, Mathematica is trying to be smart that you usually start with 1. Okay, so in this case, you're going to have 1, 2, 3, 4, 5. Right? Because I from 1 to 5. In fact, this is the same thing as saying table I from 1 to 5. Same thing. Okay? Same thing. Now, notice, and this is where it gets tricky. What if you don't want it to go 1, 2, 3, 4, 5? You want to step 1, 3, 5, like in step of 2. Well, then you add option. Basically, you just insert comma 2. Right? So create a table of I going from 1 to 5. However, don't take a single step. Take a step of 2. So it's 1, 3, 5. Right? So this is kind of like something that comes in handy. Okay? A range is one of those things where after you build this a while, people use this a lot. So people say, why don't we just have a simpler function? So the function range exactly does that. Okay? So these are very handy function, built-in function. Okay? Now, just like an array is a list, you have array is a list of lists, right, Nectar? You can also create it with function, in which case you have table. Huh? Yeah. You know what this is? Anybody? Yeah, what is it? It is a Pascal triangle, right? So this is a table of table. So it's going to create list of lists. Right? One. Have you seen this before? Right? Basically, how many ways can you get to here? 6 ways. How many ways can you get to here? 4 ways. How many ways can you get to here? Because you go 1, 1, 1, 1, right? To get to here, you have 2 paths, 1, 1, and 1, 1. How many ways you get here? 1, 1, 1, 1. This is called Pascal triangle. It's very useful, very famous. Okay? So by making some clever function, this exclamation mark is called factorial function. You don't have to care about it. The point is, see that index m to n, n to 4. See how cool that is? The big list going from 0 to 4. Now, I want to start from 0 in this case because it enters into the calculation. So I don't leave it to n comma 4. I don't say n comma 4. I don't say n comma 1 comma 4. I say n comma 0 comma 4. So n is going to go from 0 to 4. M, however, is going to go from 0 to n. So there's nothing here. 0, 1, 2, 3, 4. Right? That's my n. Inside of which there's an m. M going from 0 to n. If n is equal to 1, then it goes 0, 1. Right? So you can make a triangle array. You don't have to make a square array if you want. Okay. Now, again, this is a shorthand. Array is another word, but thread is another useful thing. All this is something that once you get to it, it's very useful, but I'm going to skip. Now, one word I'm not going to skip is called association. Association in Mathematica is the same thing as dictionary in Python. That's all I'm going to say. Okay? I use it quite a lot. Why do I use it quite a lot? Because I want to refer to rate by the key. So this is kind of a key value pair. Okay? So don't worry about it. Again, I'm just being lazy here. I'm using my Mathematica intended mostly for data analytics for this class. You asked earlier where's that underscore come from? That's the word pattern matching. Anyway, so this is how you define. So this basically are just my example, but if you go to that reference page, you just go to the core language and you also have their example. Okay, but I think mine is pretty good. Now, last thing, which is the mechanic, is if I define x is equal to 5, like I did earlier, m is equal to 3, it's going to become 3 forever. I have to clear it. Okay? What if I don't want to bother? Sometimes I create temporary value. I can stick it inside what's called module. So if I stick something in module, I'm just going to do it quickly. Okay? If I say A is equal to 5, this is global. A is 5 forever until I clear it. Okay? But if I did this, module has two parts. One is which thing I want to keep hidden. In this case, let's say A and B. Comma, what do I want to do? A is equal to 5, semicolon, B is equal to 7. Now, you need semicolon here because this thing will be treated as one line. Okay? So I close it, press enter. What happened? Well, the last line has number 7, so it's going to print number 7, right? But now, if I ask what is A, it's going to give back A. It doesn't know what A is. Okay? Because A is only known inside the body. So module is saying, what do you want to hide? What do you want to do with them while you keep them hidden? Nothing. It wouldn't say anything. In fact, this function would do nothing. Exactly. Module, you see a lot. No. That's modular. Modular arithmetic is called clock arithmetic. That's something else. Mod. That's a different operation. Yeah. Oh, maybe. I don't know. I don't use scientific help. Okay, maybe. Yeah. Is it the same thing? So similar. Yeah, in that case, it's similar. Yeah, I was thinking modular function. Okay, yeah, you're right. Yeah, so it's sort of like a little sketch pad. I used it all the time. So now, the only thing you need to remember from this basic introduction to Mathematica is in this class, you will use a lot of built-in function, comma, in particular, function that has to do with visualization, comma, function that has to do with qubit. Okay, so those are built in. Number 2, you will build your own function because you want to do a few things. You don't want to just do the standard thing. You want to do this and then do that and then do that. That's called programming. That's what programming is all about. Number 3, Mathematica has, just like in Python, basic data structure. It has, one is called just the variable itself. The other one is called a list. And that list is powerful because you can make it list of lists, right? It becomes a tensor, okay? So they don't have a built-in data structure called tensor, but you make it from list. The 2 functions that you will see me use all the time are manipulate and module. Okay? Now, this is not standard Mathematica text because people have different preference. But I will tell you that in my life, I found these 2 the most useful things ever. In fact, I will start everything with just module and manipulate. Module because I want to do a bunch of things, but I don't want to keep the result. I don't want to make it permanent. I want to make it like a side calculation. So I keep it local, right? So I can do something with A and B and then ignore it, module. Manipulate because that's the essence of control. Exactly, manipulation. Okay, and the cloud deploy, that's fancy stuff. Wolfram Alpha, that's very useful stuff. All kind of things are very useful. Chat, you can use chat inside here. You can actually even do Python code in here. One of those clicking things, you can click external Python command. So you can do everything in here. But my emphasis, you will see all the time, you have to know how to make lists because list is the most fundamental. And for our class, a list is like a vector. A list of lists is like a matrix. And I just kept telling you that your life is easy because quantum computing is nothing more than linear algebra. Well, it's a lot more, but it's just linear algebra. So linear algebra, you live and die by matrix multiplication. So you need to do matrix, you need to do vector. How you do matrix? List of lists. How do you do vector? List. Okay? So that's it. Once you got this, once you have this, everything is all fun and games now. Okay? Everything is all fun and games. So defining, so modules, yeah, for example here, right? I can do this and I don't know what that's for. I don't know why I kept that. Oh, okay. I think because I was teaching step as well. Ah, okay, okay. Sorry. Okay. Now imagine, right? You have function of x, okay? And then you have another function, g of x, right? And then you have another function, h of x, okay? And then your eyes go woozy because you see so many brackets. So to ease your vision, okay, there's a shorthand. For single variable, you just say f apply to x. That way you don't need to close it. Okay? So if I do f of x, I can do g of x, and then I do h of x. So these are just shorthand. Same thing. Why do I do it? It looks cleaner for me, but it's, again, this is a matter of taste, right? It's a matter of taste. Mathematics is full of that. It's full of personal preference. Now, another way of doing this is called prefix shorthand. I can do something else. I can say I take x, I send it to function f, I send it to function g, I send it to function h. This is called piping. This is favorite amongst computer scientists. Okay? They all say exactly the same thing. Okay? Now, the limitation is because as is, you can only use it for single variable function. Okay? There's way around for using multiple variable function, but I won't teach you now. Okay? So that's it. That's where you get this. Now the length is, if I want to know how long the list is, it's the length, right? And sometimes I just, instead of length, open bracket, close bracket, I just say length of this. Same thing, exactly. So range 9. So what do you think? So this is really messy. It's got this hash function. It's got this ampersand. It's called pure function. In if you're good in Python, this, whenever you see this hash sign and this ampersand, it's called lambda function in Python. Okay, pure function. It's pure function. It's a function with no name. Okay, instead of saying functions called souffle, the function say do this and this and this and this now, and then just show you how it's done. It's kind of monkey see, monkey do. Okay, so instead of defining y is equal to mx plus b, your pure function would be saying something like take something, multiply by m, and take that thing and add b, and don't name it. Never call it anything. Don't give it a name. So it's anonymous. It's useful for some function I want to use once and forget it. So every time you, so this, for example, you will see this a lot in my note, but don't have to worry about it. What it, okay. See if it makes sense to you guys. Okay? You don't have to worry about it. This thing, square, means I'm not going to name this, but the action is called squaring. And I add the ampersand to make it a pure function. And then slash A is called apply to each element of this. So what is going to happen is it's going to look at this, apply to each element. So what do you think is going to happen? It's going to be x squared, y squared, z squared. Now you can write this all out, but again, this is a nerd speak and they like to use shorthand. Okay. I was originally very annoyed when I was learning Mathematica that when I go to a help page or Reddit or whatever community, I get all kind of shorthand like this. You know, it's like this guy, they want to flex that they speak shorthand, like they speak the language. But it turns out once you get used to it, it's really handy. Okay? Right? So you use shorthand with any language, English language, guys, you use shorthand. Come on, as opposed to come on. Let's go, as opposed to let us go. Okay? Would you like to or do it? That, you know, you use shorthand all the time, the same thing. And means apply, except here it's applied to the next guy. Slash and means apply to everyone in the list that comes. Our ampersands indicate that this is a pure function. This is like the word lambda in Python, except in Python you write the word lambda, right? So it's just shorthand. This syntax are basically shorthand, but that's it. I think you all know. And there's even shorthand they use at, but never mind. You will see in the note that I use all this as shorthand. Now, the next most useful thing could be data set function, but not for this class. File and storage. So this is input saving. Now, this is where I want to show you this. Remember, I promised you that this is something that you can't do anywhere else. This is it. Symbolic computation engine. Okay? Symbolic calculation. So for example, all of above really is kind of like something that you can do. But this thing you can't. Oops. For example, okay. Take this. Limit, right? This is actually calculus. See, that's all this. This is all symbolic. Okay. Now, think of it this way. Can you write this in Python? Summation I from 0 to infinity. Infinity, not big number, infinity. Minus 1 to the I to the this factorial. This is all analytical. It can work even with, and this is the most important thing in our class, imaginary number. Okay? So it does that. And that's what we need, imaginary number, because quantum coefficient, right? So let's see. Now this happened to be something, okay, this is not that interesting because this is taking, now this, if you are a student of mathematics, you may recognize that maybe 300 years ago, somebody determined that this is equal to sine of x. Okay? The point is, yeah, it is that's called a tail. Yep. Now this is a cool one that I want to show. Now, took some genius, mathematical genius in the past to come up with this. So I use this as example because these are historically significant series. But look at this. This is a double summation, j from 1 to I from 1 to infinity. Of this sum, it comes up to pi 4 over 4, 120. Okay? Now, you can do summation, infinite summation. You can do infinite multiplication. That happens to be equal to pi over. So these are all famous mathematical relationship. But I want to show you that if you were not mathematical genius, you can do this with this. I don't know. What's class? There are some specialized niche language that does that. The thing with Mathematica is you can do anything from basic one, algebra, data, chemistry, and symbolic. So it's not as you don't have to go to a separate platform just to do symbolic. Okay. You can do integration. That's very good. Now this one is kind of nice because I just want to show you that if you learn if you learn statistics, you know this thing called exponential distribution, right? If you want to find distribution, you have to go to a library that come up with exponential distribution. But exponential distribution has a mathematical form, which is this. So this is actually the same thing. Equal, equal. Instead of assigning, it just says check. Is left hand side equal to the right hand side? Yes. Probability x is greater than 2, given that x follow exponential distribution with parameter 3. So this is another community called statistician that use Mathematica. They would write things like this all the time. Okay? But if you're a mathematician, you wouldn't write it like the right hand side, you write it like this, symbolically. By the way, I apologize for you tablet user. Yes, you can use this, but you have to go to here. Palette, math. Where's math? Math assistant, right? And then you get all this symbolic. Psi, pi, limit, differential. Okay, you see that? So this is a partial derivative. This is integral, derivative, and all kind of stuff. Yeah. Now, if you have a tablet, I feel bad for you. Huh? Yes, you can. Well, actually, I'll show you. If I do this, integrate f of x, okay, comma, x from, say, 0 to escape infinity. Okay, oops. Okay, what do you think happens? Well, I haven't told you what f is, so it's going to echo back. But it's going to echo back in this form. So instead of, drawing it from scratch, sometimes I would just do this, and I just substitute something else. Like, well, I want to know what... this is, again, mathematical exponential e. It's my e to the power of 1 over x. That's not converge. Yeah, that's no good. So how about 1 over x squared? So it tells you that this doesn't work. Sorry? Okay. Oh, yeah, you're right. Gotcha. Yeah. My bad. Okay, but you get the point. Okay. Yeah. So analytical engine is very important. It's very powerful. I can show you this kind of funny stuff. Now, this is another thing where it gets really powerful. Solve. Okay? I have a sound here. Ah, there it is. Again. Literally. Okay. Well, oops. Good. You see the word solve? Oh, this is another fun thing. High school student. Guys, remember the factoring homework that you did in high school? Okay. Well, imagine, okay, and this is, I'm a teacher. I'm a really mean teacher. I gave you this. Okay. I gave you this line and I asked you to factor for homework. Right? You wouldn't be able to do it. I can't do it. Nobody can do it. Well, it actually does this. It gets this. Yeah. Expand. So all this factorization, these are very important. But this is the one that I want to show you. Yeah. This one is the last built-in function that I want you to know. Okay. For engineers, maybe the word minimize would be another one. But for you guys, just say solve. Okay. Minimize would be something like solve for something that minimize something. Whereas here, solve means equation. This case, what do you think this is? Just stare at it. Hint, hint. Exactly. Right? Look at the left-hand side. I want to solve bracket, bracket. Good hint. Bracket of bracket or list of list. So basically, this is equal to A11, A12, A21, A22. Now, I haven't refreshed your linear algebra, right? That's my matrix. Dot. See that dot? See that little dot? That's a matrix multiplication of x1 and x2. Equal. Now notice I use equal because it's not an assignment. It's a condition. It's equal to B1, B2. Right? And I want to solve for whom? Because, you know, I obviously, to us, we know we want to solve for x, right? But Mathematica has to know what you want to solve it for. Solve it for x1 and x2. Okay? And you can put some numerical coefficient if you like, some real there. So for example, this one is a good lesson because I remember last time I showed you that there's a problem. There's a problem if the coefficient. Okay. This is it. This is a solution. X1 is equal to this. X2 is equal to this. And if you remember last lecture, what's in the bottom? Raise your hand. Come on. Get perfect. Automatic pass. You don't have to come here for the rest of the term. Determinant. Remember I told you? That's the guy that cannot be zero. To solve for this, that guy cannot be zero. If that guy is zero, we got a big problem. Right? Either no solution or infinitely many solutions. Either way, not a unique solution. You will get a unique solution if the determinant is not zero, and that's precisely why, because it stays at the bottom. If it's zero, then we're in trouble. Okay, so that's how it's solved. Now, obviously, that's algebraic with number, but if you can put a real number, it's going to give you a okay. Okay. So x is equal to minus 4, x1 minus 1, x2 is. Now, this guy has no solution. Why do you think that is? Because if you notice, the coefficient here is a double of that. Right? But this thing is not a double of that. So no solution possible. What does it say? No solution. Okay? What about infinitely many solutions? Infinitely many solutions because this thing is twice that, and so is this thing. So, okay? See how clever it is? Because it has infinitely many solutions, one is left as a free variable. Give me any x1, I'll give you x2. Anything will do. Okay, it's very clever. By the way, this off and on, this is just a warning thing. Okay. Now this is my function. Okay. So this is how I would do it in real life. This is how I work this thing in real life. I would say, aha, I need to work with this function. This is my thing. This is my function. It looks like this. Let's see what it looks like. It looks like this. Okay. So how do I see it? Like I said, visualization. How do I visualize it? Plot 3D. I plot my function over the range x from -4 to 4, y from -8 to 8. Everything else is extra, right? Extra option. For example, I say axis label automatic. Sorry, label y and x. So this is automatic. Okay, I can give it a name, Bob and Ben or whatever. Okay, and I can also say the label. Instead of saying hello, I just write in traditional form of what my function looks like. So it's my function, but looks in a very natural, traditional script with the script. Okay? Now, so once I've got this, let's say I want to do something. Yeah, I want to find its gradient. This is what we use for tomorrow, for the gradient descent. Okay? The gradient is to say the slope. Okay? Its gradient is equal to slope. That's right. That's correct. Okay? So, for those of you who knows calculus, this just basically say partial differentiate this thing with respect to x and y, and that's it. That's my gradient. That's the direction of steepest descent or ascent. Okay? And now, because I paid attention in high school calculus, if the function is smooth and convex, don't worry about what that means. What it means is that there's only one bottom, there's no false bottom, right? A false bottom would be something like this and like this, right? There's no false bottom in this function. Therefore, where is the lowest point? The lowest point exactly is global minimum. How do I find the global minimum? I take the gradient and set it to 0. So I set this guy to 0 and solve for the location. Okay? Don't worry about this left or right thing. Okay? Now, this happened to have 3 solutions. Well, because it's actually third order polynomial. Okay? So that's it. It's minus 2.96 something, something, something. Okay. Now, if you want the numerical, you put n in front of it. That's okay. Numerical, this is not that interesting. This is something that you can do with, JavaScript, C++, Python, everything. This numerical thing. Okay. Not that it's not useful. It's, in fact, most of the time, numerical is what you need. Semi-analytical, this is, this is final thing that I want to show you. Remember that heat equation that I showed you in the beginning, right? I just defined it, right? You remember? By the way, how do you think what's a rational for this function? It's like this, guys. This is the rod, right? And this is the temperature. Okay? If let's say this is infinitely long. This is the temperature. Okay? In time, what's going to happen? Can't. Where is it going to decrease to? Because it's got the same temperature to the left and to the right. See? Nothing happens here. Because you are hot, your friend is hot. You can't vent your bad emotion to your friends because your friend's also hot. Everybody's hot. You're in hell. Right? Now, different story. What if this is a temperature? See? This hot thing is going to vent really fast to the cold thing, right? How do you know? Because there is a sharp second derivative between them. So how fast the heat dissipates with respect to time is proportional to second derivative in space. That's the heat equation. Okay, so that's 17th or 18th century physics. So basically, you have this thing is gonna go. Okay, and in fact, one of these solutions won the Nobel Prize, not because of the solution, but because of the formulation. And for those of you who are interested in doing like financial, quantitative finance, that's where the Nobel Prize comes from. Okay, it's called Black-Scholes-Merton option pricing formula. Okay, comes from solving exactly this, except that's not why they got the Nobel Prize. They got Nobel Prize because they convert problem in finance into heat equation. Now that's multidisciplinary if you ever saw one. In fact, the person who did that was a physicist, and then maybe he just needed the money, so he started working for banks, and then thought, this problem, I can think of it as a physics problem. Okay? So you're a physicist, you work with heat equation, you're familiar with that, you walk into a bank and say, hey, this function, how can I do this? Oh, okay, I turn it into but a lot more than that, obviously, otherwise it wouldn't be the Nobel Prize. Okay? No, option price. Option price. Option price is when you have one thing that's a weekly thing, and you have another weekly thing, and this thing is derived from that. It's called derivative. And the idea is that you know this price, you don't know what this final price is going to be. Can you tell what this price is going to be? Because you also don't know what the final price. So something that looks like random becomes deterministic by the power of mathematics. Okay? So that's Nobel Prize for 3 guys. Or 2, because 1 died. I'm not quite sure. A Nobel Prize, they can't give it to you if you're dead. So sometimes 3 inventor and 2 people. This one, no. This one you got all 3. Okay. Well, here's the thing. This is exactly differential equation that second year mechanical engineering students sweat over. Okay, this is difficult. But actually, if they cheat a little bit, they can use this. They can just define it here. Now, of course, you don't get a point for this because solving is not the essence, it's the formulation. But so this is the boundary condition. It says something like at x close to 0, it's this, blah, blah, blah. So basically, just say it's cool at the end. Solve it, and this is how the power of it. Initial condition, fine. So you have initial condition. So this is the, right? So the difference between initial condition and boundary condition is, initial condition is when you set t is equal to 0. Boundary condition is when you go at both ends, when x is 0 and when x is at the end. Okay? So now solve. Okay? Now I put timing here just to show you how many milliseconds it takes. So this is called solution to heat this equation is to solve the heat equation subject to boundary condition and initial condition. Dsolve is the built-in function. Okay. Solve is just solve equation. Dsolve is differential solve, solving differential equation. D for differential. whereas NSOF is numerical solve. So this is a DSOF. There. Can you come up with that? Okay. So huh? No, that's not E. That's the time it takes, 2.71 seconds. It just happened to look like E. Sorry. I put timing because I want to show how short of a period. So the equation is, heat equation is, it has some number, it has infinite sum, it has this K function. This is, by the way, called Campo thingy something something. So basically, it's not trivial. Yeah, this has nothing to do with quantum computing. This is Gen Ed. This is to show you that you can do, in the real world of mathematics and engineering, there's engineering where you care about the number, right? And there's mathematics where you care about relationship. And as much as you can, you try to work out the relationship analytically. Why? Because if you get just the number, you don't get the insight. Imagine if Newton doesn't come up with F is equal to ma, but he comes up with numerical calculation for every mass and force. It's practical, right? Napoleon army can use that result to shoot cannons, right? But there'll be no insight. In fact, well, I don't know if you know this. Do you know why Napoleon had really good army? Well, I wouldn't say he, but I'd say, but definitely his staff knows how to do calculus really well. So they calculate the trajectory of the thingy really well. So the French army could go anywhere on continental Europe and shoot cannon very accurately. Okay, but of course, cannon doesn't feed you or clothe you. So Napoleon goes to Russia and freezes to death. That's not calculus problem. Okay, but in terms of going to Belgium and whatnot, he can shoot cannon anywhere because he solves the mathematical equation. Not him. Ballistic, yeah. Ballistic. Yeah, ballistic is basically Newton's second law and gravity, and not a lot more. Yeah. So think about it. That gigantic table is what? It's NSOLVE. Solve numerical solve. Right? Yeah. So yeah, the French army, of course, they didn't take mathematician, they didn't have Mathematica on a laptop. They literally has table of integration, and so it's, yeah, life was a lot more difficult back then. In fact, that probability that I was showing you, this exponential, this Gaussian, without this, in the old days, my generation statistic book has probability table in the back cover. Okay, basically n integrate. Okay, n integrate. But now you can use Mathematica. So that's kind of like so let me make a summary, and this is a homework, and I'll have you guys turn in by, well, let's help your friend out a little bit, those who don't have the keyboard. Let's give it till Monday evening, maybe. Okay, I will give you yeah, how about this? I will give you some homework and I'll publish it maybe Monday morning and give you 2 days, like say Wednesday, 8 o'clock. Okay, to do them. So basically, I just give some assignment that allows you to play with this. Yeah. Monday, I will publish it. What I might do is just ask you to take this thing and run through. Okay, but what you need to remember Okay, number one. Okay, so what's the takeaway? What's the takeaway? Well, first of all, QC math much less than QM math. So that gives you a smile. Okay. At some point, I will give you a little bit of insight of how that looks like, right? This is Gen Ed. You shouldn't just be able to do things without understanding. Okay, let's keep going. QC math basically comes down to matrix multiplication. Bunch of this. Okay. Number three, Wolfram is a language or syntax for Mathematica, which is analytical computation. So it does computation really well. Okay. It has bunch of built-in, like 9,000 functions, and you don't have to import like in Python. You say import numpy as np, import nvec as In Mathematica, unless you're talking about something exclusive like chemical bond, right? Something is that's you don't need to import anything. It's there. So built in, and then you user define. Now the built-in, two things that I want you to pay attention is a basic data structure, namely list, because you're gonna live and die by list. List is everywhere, right? Okay, and a lot of visualization, and the two special things, module and manipulate. Anything else, DSolve, NSolve, that's just to impress you that this is an analytical engine. It's very powerful, but we won't use much of that. So you have basic data structure, maybe association I should teach you because that's really useful. Basically dictionary. A lot of visualization. I only show you function visualization. Go to, and this is a homework that I probably won't grade. Go to that reference page. Explore the visualization. There's functional visualization, data visualization. I would say go to function visualization first. Unless you're really into data analytics, in which case, take my class or explore that. So visualization is going to be a big deal. And these are kind of like tools that I use. Manipulate to hide things. Sorry, module to hide things. Manipulate so that I can have this app thing. Okay, and that app, you can think of it as a way to give you insight. This is basically, by the way, I want to tell you this. This is my, I can tell you this was my dream when I was just your age. When I was your age, again, I was taking physics and economics, double major. In economics, there's some fairly simple equation like demand and supply. There's like ISLM curve. Well, what was tricky in economics was that the equilibrium in this graph points to equilibrium in that graph. So it's not really complicated math, but it's hard to visualize. So for me to get this insight into, how this interest rate and money function leads to ISLM that becomes a macro demand, it's very hard. And I wish, honest to God, I wish there's like it's kind of interactive visualization that does this. I never had one. Yeah, but now you can do it. In fact, I'll show you a wealth of those. So it's good at interactive visualization for yourself. In particular, this class, we should do some project. And that project should involve some visualization. But instead of visualizing anything, like we did with colors and line, we should be visualizing qubits, say. We should be visualizing quantum algorithms, say. Right? That would be kind of your project. Mini project, basically. Okay? So this thing, plus Wolfram quantum framework, again, It's a little bit like that chemical library here where it's special. You have to download. So the first time you run it, it takes a while. You go grab something from the internet, right? But this is going to do all kind of quantum stuff. Okay. So the math is easy. Be glad the math is not that difficult. This is what math comes down to, matrix algebra. And this is, okay, the tools that we use to make life easy is this. And in fact, we're going to do research with the math department called Quantum Copula. We're going to use quantum Wolfram quantum framework as a tool. Okay, so this is real research tool. So it's not just teaching tool. Okay, now this thing. So let's see what happened next week. Okay. So what's lecture 1? Lecture 1 is intro to the class, which is also intro. So the class is intro to quantum computing. So it's intro to intro. Okay. So basically, what should you have gotten from that class? Basically, my quote unquote timeline of quantum computing, right? Again, if you finish this class and I ask you who Feynman is, and you don't know who he is, then you don't deserve to pass. Because he's the beginning of the story. Right? Not sure. I'm not quite sure. I'm not quite sure. But definitely he says something like, the world is quantum, so if you want to study it, you better use a computer that's quantum. That's something like that. Yeah. It's called The World is Quantum, damn it. If you want to study, you better get something that's quantum mechanical. And it doesn't look easy. I'll give you a quote. Okay? So, lecture 1, lecture 2 is linear algebra. For some of you, it's a refresh. Okay? Number 3, besides a little bit of insight, it's basically how to work with Mathematica. Okay? Now, it's not natural to you. It definitely isn't natural to those of you without the keyboard. Okay? So get yourself one. Now, what's going to happen next class? Well, next class is now. The story begins proper. Okay? The story begins. I have to do 2 things in the next 2 classes. I'm not quite sure yet which one I'm going to do first, but let's say, okay, let's say this one is kind of like the math you need for quantum computing. Now, I already said it's linear algebra, but what about linear algebra? Linear algebra is huge, right? So what about linear algebra? In fact, Hilbert space, exactly. Hilbert space is the generalization. So the math you need for, okay, and then you have the math you need for quantum mechanics and quantum computing. And this is the slide that the infographic I was showing you. Say, physicists look at quantum experiment and then go to the shop called mathematical game store, pick out a bunch of mathematics. Okay? Mathematics of polynomial, mathematics of linear algebra, maybe calculus, maybe this, maybe that, blah, 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 blah. Pick them all to create a game that imitates life. Life is quantum. So the game is the mathematics that reflects that. That structure is the mathematics of. So I'm not quite sure. Let me think about it. Okay? I'm going to try to make life easy for you. So if math you need for QC come first, then basically it's this chapter. Okay. Yes. That Ajahn, if he comes here, okay, to teach Hilbert space, it's going to be a lot of fun for me. Okay? But it will not be enjoyable to any of you. But like I said, it's good to suffer in a safe space, right? Because I'm not going to make sure, because you don't have to make a living as a mathematician. But you should appreciate how hard life is as a mathematician, right? It's like when I send my daughter to do intern, right? I'm not thinking that she's going to learn a lot. I hope that she would suffer and I just say, I better stay in school because going to a marketing department has a lot of stock stuff and counting items and lifting heavy boxes. And so I better stay in school. Okay, so that I really want my internship experience of my daughter to really make her suffer. So it's good to suffer in a safe space. Okay, in a safe space. Right? So once we got this, I'll give you a long shot view, right? This may not take like one lecture, it may take two, I don't know, okay? And then, once we get, then the joy begins. You start to have qubit. Because once you got this, you can think of this as a heavy duty prologue. it's a slow burn kind of story, okay? Then lecture 6 or 7, you start to have qubit. You start to have quantum circuit. You start to have Wolfram visualization. Okay? But you have to hang tight until then. Hang tight till then. Okay, does that make sense? Good. It better make sense because we are out of time. Have you signed up for this? By the way, I gave you 2 things. I gave you 1 thing for Mathematica to learn. Okay? Like I said, the homework is to go through at least this page, this visualization, right? So visualization, function visualization, that's extremely important to you. Okay, all kind of stuff, right? Now, the other thing is this page. Go, I don't know what the page is. Go to internet, math. Sorry, where's the internet? Demonstration. Basically, this is a bunch of you guys, but except, probably fairly advanced guy. So think of the final project as something like this. Okay? And this is very good because it's got all kind of stuff. See? This life science computation. So let's say, I don't know about creative and art. Let's say engineering. Okay? So you go in there, there's so many topics. Electrical engineering, signal processing. You will see there's a whole bunch. So basically, this is the whole world of manipulate interactive visualization. Okay? In fact, I would use this as a learning tool. Let's say you're doing chemical engineering, go to the chemical page and play with that. Okay? So this, I don't know what this is. Constructing an eye diagram. I don't know what an eye diagram. Anyway, all kind of stuff. All of this comes in a code that you can download and play with it, just like we did before, except the button would be different. The visualization will be different. The topic will be different. And there are like hundreds of this. Okay, there's hundreds of this. In fact, one long time ago, I contributed one function in finance, but it's kind of outdated now. Okay, risk management kind of thing. So all this, so if you go to instead of nanotechnology, robotics, yeah, I had students create like robotics simulation based on this. So what happened is I say, okay, I'm going to teach you robotics. This is how robots control. Try to make a visualization, but don't start from scratch. Take some of these guys, say something like, I think he was using ARM or something. Yeah, one of these guy maybe something like this. Okay, so this is kind of like ARM manipulation. Now this one has a code. So if he wants to make something extra like 2 ARM, just go in the code and change it. Okay, and then you can do all kind of pretty or beautifying, like change the color and stuff like that. So that's all in there. So if you see that, where's the code? Open notebook in cloud. Now let's do this. Let's down the source book. Anyway, play with it. It's very good. Some authors are more generous in the explanation. Some are not. Some just give the code. The good one will say, oh, this function does this. So for example, let's see if this guy does a good job. So let's go to here. Common robots arm, enable dynamics. So let's say this is something that you happen to be interested in, and hey, where's my anyway, well, the initialize, go to see, manipulate code. See, just like you guys, just like we did, start with manipulate and then hide something module. So it's not just me that has this preference for doing it this way. Actually, I learned it from this guy, so no wonder. So all this, he defined JR, AR, AD, TD. These are things that should not be global. So hide it here, do something with it, create a table, blah, blah, blah. Even function can be defined locally. Now visualize, let's see the visualize. So grid, okay, now he's going to show something. He's going to show substring, slider. Now this is all this stuff. So basically, after all this is done, you get that. Okay, so you can do it with any kind of thing. So if you're from nano engineering, go look at nano libraries. Okay, there's a lot of stuff and gives you insight. And that thing I was telling you about demand supply, yes, go to economic page. You have ISLM thing. So this would have been a dream for me when I was your age, but we didn't have it. Okay, so that's that. Enjoy that. I'll give you something on Monday, due on Wednesday. Okay, have fun. Okay, and good luck. And yeah. Okay. ครับเดี๋ยววันนี้ขอปิดเครื่องจ๋าไม่นะลูกเดี๋ยวจะขอผมคุยกัน record